morning, everybody. This is our fifth event with Terry, and Terry is our computer scientist. And welcome, Terry, to come back to give a new talk. Right, Terry, this is all yours.
Okay, thank you. Let me get my slides up, see if I remember the correct sequence. Same topics that I've been giving for past 4 presentations. The earlier one was on artificial intelligence. And the theme's very simple, surprisingly simple. It's that information is the fabric of the classical universe, and that information is a fairly sparse commodity. If you look at most of the models of quantum physics and of relativistic physics, they assume that there is a very dense amount of information in empty space. That's, as Feynman quoted it, that's very strange to think there's so much computation going on in an empty square centimeter of space. And this approach simply drops that premise entirely and says that empty space is what is perceived to be for centuries, which is the absence of anything. That view is also very much in keeping with original special relativity, because if space is genuinely empty, everybody sees it the same. The instant you introduce a fabric to space, you introduce an amazing amount of problems in terms of how to say, why do all people see the same space? Because everybody's going to see a different fabric. That fabric has to be attached somewhere in some sort of frame of its own reference. So the techniques they do to get around that are things like colored cutoffs. You have these just amazing problems with density of information, density of the vacuum, unstable vacuums, all of these things. So to be clear on this, I'm very familiar with these topics, but the approach I've taken only in recent years is that you need to get rid of that premise. It just is more of a mathematical relic of a lot of extremely classical mathematics that originated in the 1700s before any of this came up as a topic in research in actual experimental physics. Quantum mechanics was not known when those mathematics were formulated, and they implicitly attach this information in the fabric itself. So you're talking about continuum mathematics. As soon as you say that, there's no difference between the mathematics of an extremely small piece of space and the mathematics of an extremely large piece. You have scaling, but the information density is infinite in all cases. This just is a starting premise that's not the case. Information.
Excuse me, Terry, is the slides moving? People don't see the slide moving.
No, I was just on the first one, so I will. That was kind of an introduction. So time in a sparse information universe, talking about the sparse information part. So that has impacts on where time comes from and how it works. I'm starting off in an unexpected direction on purpose, and it's a little thought problem. And many of you may have already seen this before, but imagine that you go out, nice, clear night, you go out, you stand in a field, you stand in an empty space, you don't feel anything except gravity. You've got the gravity pulling you down, but other than that, you're just there. Then you start going around in circles, spinning your arms around, and you immediately feel centrifugal force. No big deal. Everybody's done that. It's not exactly a surprise. We've done it ever since we were children. The trouble with that is remarkably simple. If you look at the Einstein definition of empty space, and you realize centrifugal forces work in empty space anywhere. You can be in the middle of a vacuum between galaxies. And if you start spinning, you're going to feel that force. So the problem that comes up is, what are you spinning relative to? If space is completely free of any kind of information, if it has no fabric to it, how can you possibly feel a force? And this has bothered people ever since Newton. Newton had a version of it with what he called a spinning bucket. Then the version that came up later was one by Ernst Mach, in which he stated a little more precisely, and said, if you take this idea that the void is just a void, you have a big problem on defining why your rotation, your centrifugal force seems to depend on the position of those distant stars. And that's an amazing thought if you think about it. You go like, how can I be connected to stars on the other side of the universe so that the average of all those stars is what tells me whether I am rotating? But at the same time, you're saying that the space in between, the space around me, has nothing. There's no field to it, there's no fabric to it. The combination comes up with an interesting paradox. And that is what Einstein called Mach's principle. Einstein was absolutely fascinated by this principle. He's the one who named it that. Mach had just had as a kind of a passing comment in one of his books. Mach, you can see the quote right here. He refers to any issue about how we're moving as an abbreviated reference to the entire universe. In the case of linear motion, you really can't even tell anything. You don't know whether you're moving or not. The case of centrifugal force is a little more perplexing because you can tell if you're rotating, but you're still going through that empty space, and somehow you're getting an abbreviated reference, as Mach says, to the entire universe. So Einstein coined the phrase for it. Steven Weinberg describes the experiment that I was just really paraphrasing. You go outside, you do a spin, the stars seem to rotate, and at that point, you feel a centrifugal force. The stars do not feel a centrifugal force. There's an asymmetry here. How is it possible that the centrifugal force you feel in your little tiny bubble where you're at is connected to all of that activity going on in the rest of the universe? And this produces a paradox. The paradox is the conflict between these two concepts. You have motion is relative only to other objects. Empty space has no texture. And again, this is why I put that as a preface in this. If you take this idea that empty space really is empty in any experimental sense, you might be able to say, well, there's some abstract sense or mathematical sense, but experimentally, empty space is empty space. No one has ever found a way around that part of the reference. You can't make empty space suddenly tell you what's going on with that. One body can affect another one only at the speed of light, is the second side of the paradox. Because if it's those distant galaxies, which are the majority of the universe, that determine which direction is rotating and which direction is not, how are they sending you a signal? How are they telling you this is what's the definition of what is rotating, what is not? Because the signal is instantaneous. You feel it the moment you start spinning. Well, it would take a few billion years for the gravity waves from those distant galaxies to even know that you're spinning. So you have that, but then you say, but what is it locally that's telling me that I'm spinning? Because the space around me is featureless. There's no information content to it. A feature of space cannot hold data about distant galaxies. That's the premise that Einstein is the one who came up with it. And yet, Einstein also recognized that there was some kind of an instantaneous link between you and the rest of the universe, that it's not a coincidence that the resting position of the average universe is the same position that determines whether you're rotating. So how do you do this? Now, and this is where the problem started, because people like Mach, for instance, Mach assumed that maybe if you had a giant, massive wall rotating around you, that it would have a different outcome. And yeah, there have been versions that when you get to the point where the wall has gravity, sure, you're going to have certain effects with that. But Mach was saying something a little more profound. He was saying that there's some connection between local, he was hypothesizing. He wasn't really saying for sure that that was what happened. But trying to figure out the resolution of this paradox has been extremely difficult and actually still has not been fully resolved. Here is a different strategy. And this is where I, as usual, I start getting a little bit outside of the standard, but in a way that's very simple. The part about spinning that is forgotten by models like that is that you cannot spin unless you have something to spin against. So you have two people here, say they're floating in space, a couple astronauts. They attach to each other in some fashion, they create a torque, and then they start rotating. Now, when you're standing on Earth, you're doing the same thing. The only reason you don't notice it is that on the Earth, the rotation that you introduce to the Earth is so minute that nothing you ever do is going to detect it. If you're rotating inside of a spaceship, you will detect it. So it's a matter of scale. The asymmetry of mass can mask the fact that you are doing these counter rotations. You're creating these rotations going one way and the other way, and that's the source of the rotation. Now, here's the radical part, and this is something I'm increasingly feel that this. I would even put it this strongly, that if you want to see why there's a lack of resolution in physics, this is at the core of it, is that too much of our beautiful maths forget the past. We ignore the past. We say, I don't want the past. I only want that pretty little piece in the middle. I only want the Poincare symmetries. The Poincare symmetries are beautiful, but what they do is they ignore the issue of how did I get there, or they treat it as trivial. You just call it a boost and leave it like that. That doesn't really work, especially on issues like Poincare symmetries. In some of the other slides, and I think I mentioned it later in this, the reason that you have conflicts on the twins paradox is the Poincare symmetries are asymmetric in where they apply. If you're in a spaceship, they apply on the interior of the spaceship, and that's it. They don't apply to the rest of the universe. It's an incredibly simple little principle, but if you see a muon coming from the outside universe, it goes through your spaceship, you will see that muon time dilate. But that doesn't mean that the rest of the universe does. What you actually see is a far more complicated thing than a simple symmetry. So if you focus too much on beauty, on symmetries, and you say, yeah, I can just ignore the past. I don't need to know where it started. I don't need to know where it finishes. I can just focus on that. It doesn't mean that it's wrong, but it does mean that you're going to have an incomplete definition. In the case of Mach's principle, the object that is spinning has to pay attention to what it was spinning against, because you cannot create the spinning without having that additional constraint. So the link to the past in this case is something very well known. It's called conservation of angular momentum. That is, you can create angular momentum in pairs. And when you create a pair, I'm borrowing this motif from the creation operator in quantum field theory. I love that operator. Angular momentum is always created in pairs. The pairs are sometimes hidden by the asymmetry of masses, but they're always there. In terms of angular momentum, which is the quantity L, you have a pair that's like a positive value and an anti-value. It's very much like matter, antimatter. So in fact, a closer analogy than you might think. So you take those two guys, the two astronauts in space, you spin them with some energy, which they provide. You get both of them rotating. And now you've created a pair of angular momentum entities that are in each of them separately. So each one has its own little clump of angular momentum that they can see. Now, here's the interesting thing. If you look at linear momentum, you can't detect it. You don't know that you've been excited with the linear momentum, but the linear momentum is still just as real. There was an excitation there also. Two astronauts, if they push apart from each other, that will impart linear momentum, and you'll have that same kind of effect only with linear momentum. The key difference is in the case of angular momentum, you most certainly do detect it. Can't get rid of it either. Once you get the angular momentum, it's there, it's stuck until you go back to the balancing force, the balancing quantity, and you do the equivalent of an annihilation operator in quantum field theory. And it's more than an analogy, because it really is the same kind of a math that's going on in both cases. Just in this case, it's a quantity as opposed to a particle. But you're taking a positive and anti, a pro and an anti, you put them back together, you annihilate that quantity called centrifugal force, and you wind up with a stationary set and additional energy. So this is, you can see where I'm getting at with this. This is part of the resolution of where Mach's paradox, Mach's principle comes from, is that if you take into account the history, you will find that it's always more complicated than just saying I'm spinning and there's no reason for it. No, you're spinning because you were spinning against something else, and you must take that into account. So this is where it gets strange, because even with that partial resolution, you still have these centrifugal forces, and you can always imagine the other partner that you just created, that you just created this with. They could be drifting off into different directions. They could go all the way over in some other spot, and you don't know where they are. You don't know how far away they are. So since you don't know how far away they are, they could be by some point a light year away from you. And then you're right back to the same problem again. You say, well, if my definition of rotation is my partner, who has the other half of the momentum pair I created, angular momentum pair, then doesn't that still violate the speed of light? And the answer is yes, that would still violate the speed of light constraint. And you'll notice in all parts of this, I'm extremely big on the sacredness of the speed of light constraint. You have to be careful, I think, everywhere not to violate that constraint. It seems to be one of the deepest principles of our universe. And we can inadvertently damage it by not paying attention to this. Now, the way you resolve that is a little curious, especially if you're and many people are in this school, and very sincerely so, centrifugal forces are, quote, pseudo forces. They're not real. They're fake sort of things. They don't actually exist. But in terms of the situation for a person who's simply drifting in space, these are anything but imaginary properties. You cannot get rid of centrifugal force by any internal operation. It's impossible. You can redistribute it. You can change the profile. You can concentrate it. But the one thing you cannot do under any circumstance is get rid of it. It is very, very stubborn. So this suggests an idea that centrifugal forces are properties of each one of those units. And that's a little bit weird, because if you think centrifugal forces are something relative to space or to those distant galaxies, the idea that you actually have to kind of focus them and they become a property of that unit of matter, such as the astronaut spinning or a spacecraft spinning, that's a rather different way to think of it. But in terms of energy relationships and the annihilation, creation annihilation, it's very self-consistent. Centrifugal forces and linear accelerations are both examples of energy excitations, and they are inherent properties of each unit of space. In the case of linear acceleration, there is no test you can do to determine that you're in that situation. You have to look at the outside universe before you can tell. Every physical property that you can measure, that's the heart of special relativity, is going to be there. You can't tell. But centrifugal excitations, the rotational excitations, those are a whole different ballgame. Those you can always tell. You can always find an internal test and say, oh, I've got spin. I am in a spun up state, and it's causing problems with this, that, or the other. You don't have to look at external stars. You can tell that by looking there, but you don't need them to tell it. It's a property of what you're doing. Now, if you go with those two ideas, okay, centrifugal force is created in pairs, but the pairs, each part has its own centrifugal force. The centrifugal concept is attached to that local object. And again, the point, asymmetric masses may obscure this, but it's always there. Then you have this issue of history again. And the question is this: how far back do those spin states go? How far back is the unspun state, the state where you're not rotating relative to the galaxy? History is critical. You have to look all the way back, literally billions of years, and say, well, if absolute conservation of angular momentum is something I can assume, which is very, very well proven, you just can't get rid of it, then this history doesn't end when I just launched out into space or when I walked out into the yard and started spinning. It goes back much farther than that. And if you trace it back far enough, you're going to find just this incredible mix of unspun and spun states and mixes of those states and crossovers between those states. But the one thing they always do is they conserve angular momentum. And that means you have to go all the way back to some extremely early state of the universe in which all of the universe agreed, this is the unspun state. This is the state we, the entire universe, are in. And that's why history is so important, because until you make that connection between all these different little pieces and stretch that history back, you don't get this idea of why some states are special, why some states are unspun. Now, I bring this up as it seemed like a bit of a tangent, but it's not. If you look at the cosmic, not at all. The cosmic microwave background also goes back billions and billions of years to near the origin of the universe. A little bit later than that in that case, because it's obscured by other issues. But it's the same kind of concept. You have this idea that there isn't a pairs of linear motion, linear acceleration, the classic action reaction pairs that Newton had. All of those all go back to an origin which nothing was moving. So there's a no movement type of origin of those. And that's what the cosmic microwave background tracks. It tells you that if you're moving in a particular way, there's going to be no net motion in what you're back at the same situation you were when the universe originated a very long time ago. I once did a calculation, I didn't put it in here. It's a particular, something like 0.2% or 0.02% of the speed of light. So it's quite fast towards a certain constellation. And if you go in that way, you will wind up being back in that original state where all of the pairs of linear momentum are canceled out. Now, the one little statement in green where I say fastest possible clocks in the cosmos, if you're up in your standard your special relativity, you should be screaming, Terry, you can't say that. There's no such thing as a fastest possible clock. And I want to point that out because it is heresy, but it goes back to that statement I made a little while ago. The Poincare symmetries apply only internal to the systems that are accelerated. You can have fastest clocks in cosmos. And when you put them all together in the end, you're going to find out that those clocks track more time than anybody else. They become kind of like the standard for that. Now, again, this is a heretical way of doing it, but it's also extremely self-consistent once you realize there's a scale issue with the application of the symmetries. Why is there a scale issue? Because they all have origins. You can't ignore the history. Poincare systems are created and they have sizes. So you have the Poincare symmetry over a certain size, such as the interior of a spaceship. So without that history, you're not going to see this stuff. CMB, cosmic microwave background, is about linear momentum. So you have these, just like the L pairs, the angular momentum pairs, you have the P pairs. And when the P pairs all cancel out, that's the original state of the universe. Very hard to find. It took people a long time and a lot of extremely good work in astronomy to figure out what this is, or even whether it existed. The fact that there's this dipole that we're moving relative to that 0 point of linear momentum for the original universe. Well, if the original universe had a 0 point for linear momentum, in which the whole universe was unmoving as an average, guess what? This whole issue about centrifugal force, if you trace it back by pairs, has the same issue. You have these same creations of pairs, just like you do with linear momentum. The pairs have certain states. The difference is these ones are not mysterious. These ones you can find very quickly. All you have to do is look for angular momentum, look for centrifugal force. If you have centrifugal force attached to your local location, unlike the special relativity case of linear momentum, the angular momentum, which was similarly created in pairs, is instantly detectable. And one of the things I love about this is you think about the cosmic microwave background as a rather mysterious thing. And yet, just sitting in your chair right now, if you spin your chair around, you are, by slowing down and coming back to a stop, you're actually bringing yourself back to a pointer that goes right back to the original state of the entire universe. I think that's marvelous. This is your your origin of the universe telescope in a nutshell, right there available to you by doing nothing more than canceling out centrifugal forces. And that's also why I say calling centrifugal force a pseudo force just seriously understates the information content of those centrifugal forces. They are telling you a lot of information, not just about where you are in the universe, but about the origin of the universe. The L null state is the original state of the entire universe, and you can find it by canceling out centrifugal forces. What this gives you, is a very different view of space and time. One is much more material focused than you might think. You have an original state on the left, like a raised plateau, which everybody has exactly the same definition. They say this is what no motion, no linear motion means. And the universe says, and this is what no centrifugal, no angular motion means. And everybody agrees. But then over eons of time, you lose that, not because it disappears, because it's broken up and dissected. Dissected is a term from geology, where a fairly intuitive term from other contexts. But the idea is that these plateaus, these mesas, every one of these mesas has exactly the same top. If you look at a certain layer, you'll see these layers go on the top. They all share that original definition, but that definition has been broken apart by the spaces that have developed in between those. Now, what I would suggest to you is that the simple consideration of how to resolve Mach's paradox, and the paradox of how Mach's principle can work, tells you something about the initial universe. It tells you the original universe was a shared state, and that it was not a singularity, because the singularity can't do this. Now, what it is exactly, that's harder to say, but it's not a singularity. It is a region in which everybody agrees, this is not moving. This is not spinning. We all agree to that. And then everybody goes their separate ways and winds up scattered across this vast expanse. That's the magic of the vacuum, is to allow these parts to go in their separate ways and go out there. But it's also a statement about the Big Bang. There's been a lot more discussion lately, and I haven't tracked all of the ancestry of some of the arguments. This would be my own contribution about why we should not think of the original universe as a point-like singularity. That doesn't explain any of this. It doesn't describe what we still see in terms of immediately obvious characteristics of the original universe. What's also interesting is special relativity also dissects space-time. Now, if you've heard this is one, this is one of the things when I started studying deep in physics. One of the last things I was interested in doing is doing saying something like, "Oh, Einstein made a mistake here. So what am I doing? What did I wind up doing?" I wound up saying exactly that. Oh, Einstein made a mistake, but it was a tiny mistake. It wasn't a big mistake. It's one of the most incredible minds in the history of humanity. And he was such a deep thinker. But there's this one little problem when he tried to fuse two origins based on a mathematical assumption into a single location. I go into this in more detail in some of my other slides, some of my other presentations. But the point is this: if you want to do transformations of time, you have to take into account the length of the system, the physical length of the system. If it's a rocket ship, you actually have to know the length of the rocket ship. Why? Because when you transform to a new space-time coordinate system, you cannot do it correctly unless you know the length of the system. And if the system is extremely large, it's going to take you a very long time to fully complete the transformation. That's the part that's missing with you have overly simplified mathematics of this. It's not a big change, but it ties the definition of time to the length of the system you're doing. This is where those earlier comments I made about Poincare symmetries, they apply in each of these colorful little cones as a people is moving, and those within that context they apply. But outside of that, no, they don't. And you have to recognize that limit. So you get the same kind of dissection based on these domains in which you have a shared definition of time and space. The difference is in the case of linear momentum, those pieces move. So the masons are moving around, but they're still sharing the same idea with this. So with that small change, and like I said, if you want to get there's a collection of three small issues that you get in the very first papers where you resolve them, you wind up with these changes, this fragmentation of space-time. But as you can see, there's a theme going on here. It's not just that angular momentum dissects space-time. It's also linear momentum dissects space-time by creating different definitions, different slopes, different angles of what's time and what's length. Jump to another one. This, to me, is one of the most underrated statements in all of physics. And the fact that Casimir is the one that said it, I just think is very unfortunate. People don't pay more attention to it from a mathematical viewpoint. The statement by Casimir, 1998, was that without a doubt, the 0-point energy has been established. I agree with that. Fantastic experiments have been done to show this is a real thing, very delicate experiments. The point that Casimir adds in that gets lost is that that 0-point energy is also the last trace of internal cohesion energy. If you take a piece of metal and you break it, as soon as you break it, the bonds between those metals are quite intense at first, but then they start fading out. So you have this whole sequence of fade outs, the metallic bonds, you have the covalent bonds. Covalent bonds fade out quicker. Metallic bonds a little bit slower. Charge bonds slower still. But you know what? Eventually, they all start to fade, except there's a little tiny remnant of energy that still comes from that separation. Casimir was saying something very profound. He was saying that in all of these definitions of quantum field theory, you can talk about infinities at the bottom all you want to, but the simple experimental fact is that all of the energy driving that is finite and extremely well defined by the forces that are left over by breaking the matter apart. And if you take that into account, it does change the math. I've looked for it. I've not found. I've found traces of some consideration of this, but for some reason, it's not a theme that seems to have caught on even after all this time. So this is what 27 years later. Hasn't really caught on that quantum field theory needs to stop assuming infinity is the bottom and pay more attention to the source of the energy, which is this last bit of the cohesion energy. As soon as you do that, your hopes for infinite energy from a point of space, just disappears. It's just not there. This version of the Casimir force by Casimir does not do that. Can't do that. When I first came up with that metal breaking argument, by the way, I did this independently, and I was surprised and delighted when I found out that Casimir had used the same argument, because my argument was in contrast to some of his early papers I'd written, and then I read that and said, "All right, cool." He absolutely confirms that same idea. So this also adds to the idea of fragmentation, dissection, because it means that the quantum field theory of all things is also created and constrained by the bonds of matter, not by space-time. As soon as you go to infinitely smooth space-time, which is a 1700s concept of mathematical infinities, but as soon as you get away from that and go more back to the Taylor series, where everything is an approximation, it's only finite to the limits of energy you have. I love the Taylor series. The Taylor series is in many ways the resolution to a lot of this. The Taylor series is more realistic. It says, okay, I can approximate those things up to a point, but then it stops. At some point I reach a finite limit. So you don't get a full set. You never complete the set. It's always an incomplete set. So the mathematical beauty of that limit is not well supported by the constraints of matter. You only have so much matter, and within that matter, you can only stretch it so far. Whereas if you assume a smooth space-time, then you're cheating, because you can do whatever you want to. If you assume a smooth fabric that goes to infinity. This would be interesting to see if there could be more development of that. I would also add to it, when I use the word mature, at the bottom line there, mature inertial units, it takes time to create a new instance of space-time. And now that sounds heretical, but it also is anybody who's actually worked with satellite systems, they have to put this into their equations. They can't just assume this because there are delays of light between the different satellites. And if you don't take into account the fact that you have to coordinate those before you can come up with a common definition of time, then you won't get a correct answer. You might have a you might be guiding a car and drive them off the side of the road because you didn't give the right coordinates into their machine. So it's an important point. It takes time to create these things. Vacuum shattering, meaning shattering using the vacuum. The idea of the vacuum is something that shatters an original version of the universe, argues that there is this concept of a compact shared universe. And one of the hints I would give that is I would not even say that this compact shared universe necessarily exists in a version of space as we think of it, because as soon as you start creating space as we think of it, you wind up breaking it. So there's a kind of an inverse correlation in that. But it does say there's a sort of a deeper definition of very common things, such as what is an unspun state, that nonetheless they were shared, but then it was broken apart. So this idea of a vacuum as a way of shattering these different pieces produces this really interesting clumping, acceleration, despinning, locally rebinding, returning the earlier state. You get these commonalities. You get this idea that an electron on the other side of the universe looks exactly like an electron on this side of the universe. Well, that's a very strange thing. But if you have this idea of a compact shared universe in which you have compact in the mathematical sense, it's a single unity, and that we're just looking at the shattered remnants of that, it makes more sense that we have these remarkable commonalities across the university. It also just makes life and complexity much more interesting because you can do all these different breakings and reattachments and putting them back together. Final point in that, some of these properties don't shatter fully. Guess what happens in those cases? Surprise, surprise, you get things like electrons going through two slits at once because the definition of space and time is a shattered event. That's one that's broken into these different pieces. But you can still access some of this deeper underlying state where it does not follow those rules. There's a form of unity there that you don't see once you break down into some of these little mesas of a particular definition of space, a particular definition of time. Speaking of time, wasn't this talk supposed to be about time? Well, the reason I'm going through all this is that time has to be attached to material components, and the material components are broken up in a vacuum shattered universe so that you have the quantity of time starts from the bottom of phenomena. How far down, bottom does it go? Here's a fairly recent quote from Roger Penrose back in 2016. Why are clocks so precise? There's a little equivalence that this is also in Feynman. Usually I've used Feynman as my quote for this, but Roger Penrose had a marvelous little quote that I thought captured it much more compactly. There's a famous equation, E equals mc squared, but there's another famous equation that was E equals h nu. I'm sorry. Nu looks so much like V. H nu. That's Max Planck who came up with that. And it says that energy is also equal to a frequency. So you put those two together, and what you find out is that every version of mass is also equivalent to a version of frequency. And when you define a frequency, you have defined a clock. Simple as that. So what is the simplest possible clock in the universe? It is a particle. It is any kind of a particle that's sufficiently stable that it can persist. And the frequency is like a repeating loop. And here's another interesting point. It's if we talk about a spin one particle or spin one half particle, that loop is also one of those plateaus that I was talking about from the CSU, from the compact state universe. That means that even the idea of a particle spin is also referencing back to this original state of the universe. There's a connection there. It knows what the original spin state of the universe was, and it chooses to be spun in contrast to that. That's part of the definition of what a particle is. It's also part of the definition of what time is. Until you get these little repeating loops, you have no concept of time. No, the idea of a smooth time as a geometric dimension, that doesn't cut it. That doesn't explain what time is. That's one of those overly beautiful abstractions that actually undercuts the idea of finding out what it is. You follow Roger Penrose's route and say, what is it exactly? That's getting to the heart of it. It's a loop, it's a frequency, it's an angular momentum. It is something that breaks this original, to add that thought, CSU plateau. One point I would like to make about this is if space-time is shattered, if it's local, if instances of space-time, and notice, just because I say space-time does not mean that you don't have change, doesn't mean that you don't have distance. Space-time is a very specific information-rich version of change and of separation. And that's a key difference, because without that information component where things become sharp, become well-defined, the idea of space-time the idea of time and the idea of change without that, the idea of separation without, doesn't buy you much. You still have just essentially a chaotic universe. Our universe gives us something much more interesting, which is these space-time constructions that are energy rich and much more precise, but they're also bottom up, because the time starts at the particle level. Whatever is making particles spin, that's the deeper origin of time. And that's not the way you'll usually hear it described. So, but I would stand by that rather strongly, that's your source of that. But it also means you can start building up from that. So if a particle is an instance of shattered time, what is a molecule? A molecule actually has its own local little definition of space and time, which is completely in keeping with the larger definitions we usually use most of the time. Emphasis on most, because if you see, again, phenomena like the fact that you can make even large molecules self-interfere, they're telling you that it's not, those definitions of space and time are not completely universal, even at that level. If you also look at what advanced chemistry can do, some of these things play games with what we usually think of as space-time perception. Usually when that happens, we put it in the moniker of quantum computation. It's one of the reasons why I'm adamant that if we need to understand quantum computation at the molecular level better, because that seems to be how life does it. Life does not use big cold units frozen to almost to zero to get just a few bits of quantum computing. Nope. You look at some of the early papers, Hopfield, his papers from 1974, where he talks about how out of chaos this beautiful unity suddenly emerges. That is weird stuff. And that's where I would say that part of what's going on there almost certainly is this idea that they're creating units of this space-time constructs that aren't doing reality quite the way we think they should if we impose a giant, all-encompassing definition of space-time on it. So I would point out that has issues. One of the most famous unresolved issues, as far as I know, it's still unresolved. How does high temperature superconductors work? Now, I would put this out almost as a wager. I wouldn't wager on it, but I would put it out as a bet, just saying I think this will eventually come out to be the case. I suspect high temperature superconductors are much better described if we start playing games with the definition of space and time at the particle and molecular level. That is, we're playing with particles that are creating their own little definitions of how space and time works, and those are interacting with other units. So I think high temperature superconductors is one of the more likely areas where the idea of microscale space-time could be a useful tool for making sense of some of these things. Quantum computing, same thing. Um, some of you have heard me. Qubits are fine. Okay, fine. Qubits are fine. Okay, right. Okay, you do qubits, but I just continually would argue that qubits are one of the weakest paths possible for getting at what molecules are doing. We should take a hint from the fact that we require what, I don't know, tens of thousands of qubits to emulate one molecule. Think about that. Maybe we got that backwards. Maybe we should be using one molecule to emulate tens of thousands of qubits. In other words, have a little bit better control of how the molecules do their computations and borrow that. That's more the Feynman path towards quantum computing. And where these, forget the nonsense that came, and it is nonsense, that came out of Hopfield networks. Go back to his 1974 papers. Those are the interesting ones. Those are the ones that say something, because those are the ones that talk about generating order out of chaos. And I think insufficient attention has been paid to some of that. I'll wrap this up with a specific example of a phenomenon that I think a space-time, micro-space-time approach actually makes the analysis easier. It's not the only way you can do it. It is always would have equivalence. Just because I'm suggesting the radical idea that you break space-time up into little pieces, it doesn't mean it's incompatible with the math we have now. It just says that you can represent some things more efficiently and more easily. In some cases, maybe just make more sense if you use that approach. In this particular one, chain fountains. People really get excited about chain fountains. It blew up on YouTube a few years ago, and Derek Muller and Veritasium and a few other guys I've forgotten the name of the guy who came up with it, but Stephen Mould. They were all Steve Knowles one who uncovered this, and everybody's just kind of going nuts saying, how does this actually work? And coming up with all sorts of elaborate theories. If you recognize that linear momentum states are instances of space-time, and you recognize that angular momentum states are examples of space-time, instances, both of which have been excited in different ways, and you look at a chain fountain, you have three conspicuous components. You have the blue linear upwards linear momentum component on the left, the right descending linear momentum component on the right. And according to a space-time interpretation, those are separate instances of the space-time definition, which can carry a lot of energy. The top one is the interesting one because you have a half loop, not a full loop, but a half loop of the angular momentum version of space-time. And the half loop becomes like a soliton that's riding on the matter that generates it. The matter flows right through it, but then that little instance of space-time has a certain persistence to it. And that persistence gives this very interesting levitation effect where you watch this thing just rise up into the air and kind of defy common sense as why should it be rising up in the air? And like I said, you get very complicated explanations. I would suggest that this is an instance, a very visual instance, where a space-time, micro space-time approach, and particularly the idea of micro space-time solitons, little bits of space-time, of energized space-time, that are riding on a wave of matter, but they're not actually attached fully to the wave of matter, can give you a simple way of explaining this. This is also one of the reasons examples like this on a smaller scale that I think somehow have got to be connected with some of these superconductivity issues, that there's little loopy things going on where you're creating extremely small instances of a particular type of space-time with its properties and conserving the energy. That's somehow helping out with that. Now, what that would be, no idea. I'm not saying this is something that's easy to figure out, but I think that would be an interesting tool for trying to deal with that. Summary. And I'm keeping it under an hour. All right. Time and space are secondary relationships. Cannot, I mean, if Terry had his theme to leave and say, this is the one message that I would want to get out to people, is that time and space, the precise forms of change and distance that we call space and time. Again, not the same thing as change and separation, but time and space with their very precise information relationships are generated by matter. With no matter, you don't get them. They don't pre-exist. There's no fabric of generalized space-time. I know that's very popular with a lot of very, very smart people. And it's something we're trained in that's this mysterious fabric of space-time. And there's some good reasons for it. It can be curved. It can have, how do photons cross it if there's not something there? The trouble is that all of these things, when you talk about the curvature of the fabric or the photon going across it using quantum field theory, all lead to interesting paradoxes in which you lose this key insight of special relativity, which is that space is featureless. So you wind up with substitutions for that in which curvature of space is a set of very special relationships between particles of matter. And then without the particles of matter, you don't get that. Obviously, that really has an impact on issues like black holes, because it says that black holes still have matter in them. That what's going on is that the event horizon surface, and that it's not going on the interior. Externally, it looks the same. You still get the same black hole. Light still goes back into it, but it's still a different way of looking at that. Time begins at the particle level and then self-organizes. So that's a very different way of looking at time. I'll get into my next presentation where I talk about particle physics more. I think there's some extremely interesting issues there about just how time emerges at the particle level, because it involves incomplete attempts to create time in different ways, and then they kind of get together and create something interesting. Information is sparse. Maybe that was the second message I would want to be out about. Information always requires machinery. Now, my computer science background absolutely shows through, but also I'm just saying this is what we see in physics. We don't see infinite storage information in a vacuum. It doesn't happen. And this is one of the reasons why Feynman said, he says, probably something simpler like checkers. I love that. He got a good laugh when he said that. But he meant it. He was dissing his own theory. He was saying that, no, there's something not right about this. And this is where I think it is. The sparseness is that matter is the generator of all these phenomena. And it's not just raw mass. It's very specific constructs, fermions in particular. The massive fermions and how they work, and the fact that they have two chiralities is really interesting and important. All of those work into this idea that time is a complicated, almost magical quantity that emerges, and once it does, it allows our universe to exist as we know it. But don't assume it as a given. It's not just a little thing. Information, same thing. It requires something to create it. Man, the vacuum is empty. How light crosses it, part of the giveaway is, well, how does an electron go through two slits at once? The answer in both cases is the same. It doesn't in either case. It goes through using the physics of the compact state universe. It goes through using something that we don't perceive as ordinary space and time. We're not totally separated from that compact state universe. It's still there, both in terms of its lingering dissected legacy, but also more directly sometimes when we do certain weird little things. Now, here's something that'll get me in trouble with mathematicians. Symmetry maths that disregard history are incomplete. You will never, no matter how many groups you go through, you're never going to find an explanation for the universe using symmetry maths. Sorry. Why? Because symmetry maths always disregard history. It's as simple as that. If you can't eat the center out of the pie and claim you understand what a pie is. It doesn't work that way. If you don't follow these chains back to the origin, if you don't go back to why everything locally has a definition of what it was globally at some time in the past, your math is not going to be complete. And all of the symmetry maths are fascinating phenomena that emerge locally and incompletely from these deeper physics. So if you ask, why does the universe exhibit certain SU3 symmetries? That's an extremely interesting, very important question. But I think we've locked ourselves into a dangerous paradigm when we say that that's the origin of it. No, you want your maths yourself, you want to look into them historically. You want to say, where does this symmetry come from in the math? What is the origin of these symmetries? That is where I think the symmetries will again take on a more important role. But as long as we try to explain the universe this way, you're stuck. You're not going to get anywhere because you didn't pay attention to the full problem. You just can't get around from that. Final point, micro space-time design, which is not something, this is a concept I'm proposing, but I'm also, I gave the fountain, the chain fountain as an example on purpose. I'm saying that I don't think it's intractable. I think we can come up with ideas like space-time solitons that are energized. And I think the idea of energized space-time solitons could actually turn out to be quite important as a new way of approaching structural chemistry, as a way for explaining some phenomena that we have difficulty with right now in solid state physics. With that, I believe we are a wrap. So, time for questions, I think.
Yeah, I noticed George has a question. And can George unmute and ask a question?
George,
Or I can read out the question. My understand if information is limited to reading Shannon and Nyquist, there's a source of information, a receiver, and a noisy channel in between. Also, a finite smallest time resolution, which implies a maximum frequency, which can be resolved frontier transform. Curiously, the relation between time resolution and frequency resolution is like Heisenberg's uncertainty of non-commuting operators. What does information content of space even mean? Is it intensive or extensive?
Oh, there were a lot of interesting comments and questions in that, but I didn't catch quite all of them. Yeah, can we have like a one sentence question from that? George, are you still there? Let me see if I can bring up a copy of that. I need to be able to see the question in a little more detail.
It is in the chat from Georgia at 12:17 p.m. It's a long question. He has two
Yeah,
questions.
it's a lot. Yeah, I say very interesting question. Uh-oh. Did I just lose you guys?
Uh, I can still see your screen.
Okay. Oh, okay. All right. That was something else I was going to warn you from. Still trying to, maybe I need to unshare I'm not sure. Maybe I need to unshare my screen, but I'm not quite sure how to do that. Okay, now I've got more where I can hopefully get to the question. All right, so George Zipperlin. Okay, I see the question now. Unmuted read Shannon. Receiver.
Hello, can you hear me without a lot of echo?
Yeah, I hear a lot of echo. Maybe you can dial in over the phone.
I love your question, but that is something I have to think about. And the fact that there's a connection with Heisenberg uncertainty principle. Oh yeah, because one of the characteristics of our universe seems to be that it has enabled information to exist despite the uncertainty principle, and that's intriguing. I think this whole diet of how we break up into different pieces is related to how this concept of information comes into existence. One of my statements I made in previous things, I'm not a a universe simulation person at all. In fact, I think just the exact opposite. But I'm very much agreeable with the idea that the classical universe that we see right now, that is around us, that behaves under certain rules, that is composed primarily of information imposed on top of a much stranger universe, this CSU universe. And it in some fashion, we don't understand this ability to fragment and break apart also allows us to create information that persists for remarkable lengths of time, starting with the fermions. Fermions are extremely durable. They are the starting point for information preservation, but they also have a very odd relationship to this compact universe. They're in contrast to it. They break apart from it. They have a spin. They insist on having a half spin, whatever a half spin is. And in doing so, they allow this persistent information that you then start building other things on top of, but always within limits. If you have a very small amount of matter, you're going to get intensive uncertainty because you can't construct really stable information anymore. See how I flip that around backwards? We usually think of it saying like there's infinite information there and somehow it gets chosen. I'm saying no, it's just the other way around. That you don't have enough capacity to create the solid information. So you default to a different set of physics. And that different set of physics is not trivial and is interesting and actually is the source of some of the things we call like quantum computation. So they both have value, and we would like to access that deeper thing a little bit stronger. So, but I love your question. And the idea that there's a sea level, yeah, I'll just have to think more about that, but that's a good question. Follow up or anybody else?
Terry, can I ask you a small question? Maybe I haven't understood fully your earlier slides when you're talking about the centrifugal feeling when something is spinning and the connection with the earlier universe, unspun universe. So if you say there is no violation of light speed, what does it connect the earlier universe, unspun universe, with present spinning, in a sense? It's a kind of entanglement. And what is the actual mechanism of that connection?
Let me answer that in two different phases. The first one is the simple one, using purely classical terms and saying it's a tree. You have just like the plateau example I gave, where you have a plateau, it gets broken apart, the pieces still remember that. So that's a simple answer, is just say that the fact that we know what is the unspun state is easily explainable if you go back and say the history of it. You say, well, absolute conservation of angular momentum requires the original state of the entire universe, whatever that was, to be still have its little traces going all the way out to what we are right now. That's the real resolution of Mach's principle, because it does attach it to the immediate unit that you're talking about. Now, that's the first level of an answer to that. But the second level, I think, gets much more interesting, because I keep talking about this compact state universe and how it can pop up, for example, in quantum mechanics. And that universe doesn't obey those rules. That universe, this is the whole issue of entanglement. That universe does violate, in some sense, what we would think of speed of light. But the catch that's been known for a century now is that the violations do not involve information. It's when you get into the information, which is the fabric of the classical universe, you get this incredibly severe speed of light limit. But if you go below that and say, like, why is my electron exactly like the electron on the other side of the universe? You can kind of explain it with the fragmentation argument. In fact, I think that is a big part of it. It's another example of a dissected property from the original universe, which was not a singularity. And you can sort of explain it, but also there's just a persistent, deeper connection there, that in some sense, all those electrons are still close to each other, and all this separation fabric we have built on top of that is a bit of an illusion. So, it's something that by the fact that we consist of information, we also simultaneously lose our access to that deeper structure, mostly. So I think it's just a fascinating interplay going on with this, that we have a universe, the CSU, that is not like what we think, has all sorts of conservation. Pair conservation is just a critical part of it. That's where a lot of the complexity emerges from that. But our space-time universe, this is something I've said in other talks, the definition of length, for example, or separation, for instance, probably resolved to some kind of a frequency concept, a repeating concept in that deeper universe, because that's how we get separation between radio frequencies. You have 1,000 orthogonal dimensions of radio frequencies. And how do you get to them? And, they're all going through your room right now. You get to them by tuning into the right frequency with that. I think there's good reason to think that the concept of length that we have underneath our universe at some level also resolves into frequency Fourier transform relationships. But those relationships are emerging from this deeper universe. So you have like a consolidated thing that certain parts of it starting to say, I'm going to vibrate this way. You good with that? And they kind of get together and, bang, quite literally. You get this emergence of time on a much larger scale in this universe we see.
Are you saying that earlier phase of the universe, or during the compact shared universe, the laws of physics and the laws of physics that we have now have changed through time, or they are invariant throughout whole history of the universe expansion?
In that one, I would actually say that the CSU is I wouldn't state adamantly that it's invariant, but it's extremely conservative. In fact, I would not say that it's invariant, but I think it's almost like a game. If you can imagine that this universe is frothing around with its different definitions of frequency and of pair production, and at some point, enough pieces get together that they create a consolidated concept of time, one that is sufficiently strong, sufficiently large scale, that the darn thing blows up, that it just literally, the time shoots off in this one direction and says, bye-bye, I want to do my own thing for a while. And since I'm a dual universe person, I would have a controversy that goes off in the other direction. You can look for Turok and Boyle. I have a lot of good papers in that, much deeper on the math, but I use quaternions. I don't use, which are a little bit like this, some of Roger Penrose's ideas with his, I would not, and I'm getting off in the dual universe. You need a consolidation. When you get the consolidation, you get the emergence of time, but it is not infinitely stable. So yes, eventually some of that's going to change, but there's also a huge amount of unity to it too, that the change is extremely slow. An electron is electron is electron. And there might be other fundamental particles that don't change, but eventually I'd say those universes are going to loop back on themselves. And at that point, you're going to get a lot of change. It's going to have some kind of annihilation that changes many of the properties we think of. So very stable, but not infinitely so.
Yeah, thanks a lot.
I noticed a question from Dr. Duda. He said the water chasma, but requiring a shaker. What is it in particle physics? Particle clocks themselves?
I'm sorry, I didn't quite catch that. Could you repeat it again?
So this is the remark, but you have also mentioned that the question is what is the shaker in the Casimir, and I think you have agreed that the particles that themselves are the source of this energy for
Shaking.
Casimir.
You're very interesting. Yeah. You've got Dr. Duda has an interesting theory about the source of the oscillations and the frequencies. I would tend to defer to you on something. I think you have some interesting ideas on that the frequency itself is part of the source of these oscillations. So Yeah, that's a good question, but
I think you have also mentioned that the particles themselves should be the source, but the big question is what propel the particles now. So this is shifting the problem to the particle, and so in other words, why the resting particle is already oscillating. So why is it the time crystal? You can say, as
one
I
of the
have discussed last time.
yeah, well, yeah. Oh, that's interesting. The one of the things I get into, and I'll get into the next talk. I think it's next month, July. Uh, is if you look at the composition of the color force. The color force has this interesting thing where the three colors together, there are three forms of pair production that they kind of go in their own directions. Now, I proposed as a hypothesis that there is a direct link between charge type and time axes. And one of the things I think is going on at that level is that the oscillation is emerging from three orthogonal definitions of time that just kind of get together as the color force, and then come together as a neutral color that we call the electric charge. So,
But you need to start earlier. Electron is the simplest example. So
actually,
electron
no,
doesn't have.
I would say the electron is not the simplest example. I think the electron is one in which this process is taking place more in that deeper universe. The proton brings it out more in the open, because when you see a proton, you get these three axes. They're trying to produce pairs, but they said they wind up in a loop, and they're just kind of. And I think that loop is the kind of like the critical invention that came out there, is this idea that the pairs say, oh, we can loop up. We can actually form, at least three steps in doing this kind of forming a spiral type of motion. And I think that's where part of this oscillation comes from, is that the deeper structure of that is the pair in creation annihilation. That is certainly one of my deepest premises, that most of what we think of as these emergences start with pair production. And again, you got to start somewhere. Obviously we have a universe, so I had to start somewhere. But creation annihilation, if you have competing definitions of creation annihilation, and at some point they kind of get together and form a loop, I think that has something to do with the source of your oscillations. In the case of the electron, I think I think we're getting an interplay at the electron. A positron is a symmetry of the proton that is structurally more compact in our universe, whereas the proton is the uncompact version of it, where pieces that were going on in the compact universe are actually exposed in our universe. So while it's very standard to think of the electron as the simplest particle, I actually think of the quarks as giving us more insight into what's going on at a deeper level, because of that marvelous cubic structure they form. That cubic structure gives
the electron is the lightest charged particles. We can say that. Yeah.
Yeah. Yes. I also, we talk about rest mass of quarks. I don't think quarks have a rest mass in the usual thing, because I don't think they can rest. I think they're incapable of ever stopping. They just move. The reason that electrons are capable of rest is our entire universe is moving as a collaboration that we define as our definition of time, and they're just coasting along with that wave. So we're just looking at, we're all surfboards in the same wave, so they look like they're stationary, but I think actually it's a much more interesting dynamic going on.
So generally, there is charge quantization, and then the simplest charge becomes electron. So I think we just need the charge quantization mechanism is much simpler, explaining why the Gauss law cannot return any real number but integer multiplicity of elementary charge. And this is relatively trivial for topological, and having that, you have electron. Then for quarks, you somehow break these constraints. So this charge quantization. So there is created these quark strings between the quark and anti-quark, and which is very costly. Which is like 1 GeV per femtometer in QCD corner. So you can bend the charge quantization, but it's costly. You need these quark strings between them, so it is very costly.
And the thing I would point out about the electric force is, if you look at how our universe is constructed, we too are set up from bound pairs. We call them atoms, hydrogen atoms, because they are the bonded form of the electron, the negative charge, positive charge, with a twist. And the twist being that one of them has this compact representation, the electron, and the other one, the proton, has this non-compact representation that has an actual physical volume in our universe. And I actually think one of the reasons why our universe exists is because the wires got crossed, because we have a universe in which the positive charge is mostly implemented using this other technique, but it's the same positive charge. And that implies there's some structure underneath that. Then the electron has a different way of doing it, and they can't combine anymore. And that's why it's part of why we exist, is because the darn things to say, like, I can't cancel your color charge. I can't cancel your hadron-ishness. I can't violate that. They wanted to cancel the charge. And the fact that they almost cancel the charge gives us this marvelous opportunity for complexity, because then they're mostly electric and neutral. They can break apart. You can have these massive separations, but it's still a pairing. It's still a pairing of those charge types. And the quarks, I think, have a different kind of pairing that's much more dynamic and gives us some insight. So whether it's a break or an emergence, I'd lean towards emergence, but I see what you're saying, and I think you've got some fascinating ideas, like the electron neutrino resonance also with that. So
they have the same charge. So if you take Gauss law around electron, positron, and proton, you have the same. However, the energy is much larger for proton. So they are both configurations, stable configurations of field. But somehow a proton is heavier.
yes.
So we need to explain that. So what is the difference? But I think you need a field configuration. You need a Lagrangian, and
Yeah. No, I'm actually suggesting that the theories that say that it's just an accident that the proton charge is the same as electron charge, I just would discard
no,
those.
this is
Yeah,
charge quantization.
yeah, that doesn't that makes no sense.
Nature has charge quantization, so this is the reason.
Yeah.
So you cannot have half of electron. You can have 1/3 in quark, but it's a very high cost, and this quark strings between them, which is 1 GeV per femtometer.
Yeah. The point about the proton, why the proton is so different from the positron, the I guess best way to say it is, I would just go back to one point. I think there's an incomplete. We got two universes going on here. We could like say the CSU universe that doesn't follow our usual definitions, and we have this spatial universe. Protons, most of their innards are in the spatial universe, the one that we have. Electron, most of their innards are in that other universe, and they're the more pristine version of it. So the proton would be a broken, the quarks and the protons would be a broken symmetry in that sense of coming out of that and being forced into a representation that they don't really like. But it's also very beneficial to us, because that very violation, breaking of that is what allows atoms to exist. Hydrogen atoms are an amazing thing, just absolutely amazing, because I mean, think about it. We didn't have hydrogen atoms, the universe would be annihilated instantly by electrical attraction. If we didn't have a mostly neutral universe in which most of the charge is canceled, none of this could exist. So the hydrogen atoms do a double service. They persist. They're stubborn little things. They don't give up easily. And at the same time, they're also mostly neutral. And almost cancellation is just an amazing thing, because almost cancellation just allows the emergence of all sorts of complexity. It allows
So it brings another question. So what is the difference between the hydrogen atom and the neutron now? So this is also very similar. Some people try to model neutron as a tiny hydrogen, but
you know where I'm going to go with that. I mean, neutron, neutrino, electron, positron.
it's very different. The neutron is very light and producing beta decay. So you need to get the beta decay from neutron to proton, producing neutrino.
Well, but I was saying, what I'm suggesting is neutrino, going by the same symmetry argument that I was saying earlier, that the proton is a broken symmetry with emergence of mass from a deeper version that is like positron. The neutrino, I would suggest, is kind of the same thing, that it is a version of the neutron is a version of the neutrino. I mean, shoot, the name even says that. I mean, when they first came up with neutrino, I know.
So no, the neutrino is very, very universal. It's much lighter, so it's
Yes.
many orders of magnitude lighter, and it's produced during the beta decay.
Yeah, and the neutrino
You-
has no, of course, fascinatingly, has no mass and has only one chirality that we can detect.
So it is assumed that it has very tiny mass, but I think it's complicated. But you need
Yeah.
neutron, proton, and transition between them, producing neutrino.
Yeah.
So generally, you need field configuration. So you should try to write some Lagrangian, draw some field configurations. But yeah.
Well, the neutrino, yeah, no disagreement. I think this is some very interesting. The emissions, the conversions of quarks from neutrino emission. You know, you look at the proton and how does it get converted into a neutron. You really have to look at those interactions between.
So muon decay also produces neutrino. There are no quarks. Muon decay. There are also produces neutrino. There are no quarks. There.
Yeah. Yes. There's no quarks in electron either. So
Yes, exactly. So we need something universal for neutrino and very light and so you need to think about the entire process. You need to draw some field configuration of neutron, proton, and show that evolution between them produces neutrino. And they are much more universal. So not only here, also muon decay and so on. Okay, thank you very nice talk. Maybe let me leave for somebody else.
Derek, if you haven't looked at that double cube diagram that I do sometimes where I show that, the weak transitions are the vertical lines between the two cubes. They show all those relationships that you're talking about, where you have these transformations. You lose a unit of charge, you go to the polar, the other cube, you transfer between the cubes. It actually is, you could make an argument that the standard particles of the standard model are actually hyperspace links between these two cubes, because when you put two cubes linked to the cornices, it's corners, it's a hypercube. And
So we have
all
field theories.
all the
There is
fermions.
electromagnetic fields. What is the configuration of electromagnetic fields of your particles?
In that particular, if you have those two cubes, the electromagnetic field is the vertical direction. It's a direction as opposed to so.
Please try to draw field configuration, especially electromagnetic, of your particles. So this is what we could compare with, but yeah. So you need more mathematics, Lagrangian field configuration, and yeah, sure, discuss.
I think I like your work. I like your ideas. We could have more conversation on this sometime. So
Yes, but we need some concrete Lagrangian field configurations, and we can discuss them. Okay, thank you. Have a nice. Thanks.
any other questions?
Yeah, I saw a question, but the participants are not online right now. The question is Einstein's equality is about rest or inertial mass energy equivalence, while Planck's equality is about massless photons frequency. How would the two meet in the same frame of reference and claimed to be somewhat equivalent?
So this is this question is in the chat?
Yes, it's at 12:44 p.m.
12:44. From Emre. Oh, from
Yes.
from the one from Imre Coxon, or from Jared?
From
Oh,
Kosovo.
yeah, Imre. Okay, from Imre. Let me see. Let me take a quick look. Well, that's a good point, because that Einstein's when the equivalence in that particular equation that I'm tempted to the idea of a frequency of mass equal to frequency is extremely well established, I think, both experimentally and theoretically. Roger Penrose's particular ones, I think that's an interesting, I'm going to blame Roger Penrose a little bit. He made his equivalence system. What would be the equivalence on that? Because in one case, E equals mc squared, you're talking about rest mass, but you're also talking about the gravitational mass. Feynman uses a somewhat different argument for describing the relationship. In both cases, they wind up with a mass frequency. I think that's a really good question, and I would have to go back and look at Roger Penrose's. You can tell I'm intentionally passing the buck a little bit and look at Roger Penrose's version, because he was talking about essentially photon energy being equivalent to rest mass energy. And yeah, I have to look at that. I might go back to Feynman's argument instead. Good catch. Other questions?
Sir, if I may ask again, is this idea of this compact shared universe, and you're saying that singularity is out of question. So I'm supposing that the compact shared universe was a kind of a symmetrical state of fluctuations. Now, what broke that symmetry? That's the fundamental question. And how it was just a kind of a fluke event of the nature, or is there a possibility that the thing can happen again and again and again and again? The higher probability of this breakage to reoccurring.
That is, yeah. Let me see if I can bring up. Give me a minute to look here for a slide. That's the wrong one. Of course, I had some slides ready, but I didn't have that particular one ready. Well, instead of spending time trying to look for that, I can't find the slide. There's an earlier presentation, actually from several years ago, that is called quantizing on quantizing general relativity. It's at my Apobistia notes site. And I think that is just an incredibly interesting question. And my own suggestion for it is that I think we have sequences of emergence, that it's not just one emergence at all. That figure I'm looking for is the idea that we have first one version that sort of gives persistence at a low level, but the forces that we see now are not broken apart. You'll see some similarities, the idea of emergency from a singularity, but it's not. The difference is this is sequenced, and it's not just a singular. Everything's floating. But the idea is that you get a little bit of persistence, a unified set of forces, not at high temperatures necessarily, but they just have no distinctions between each other yet. So when we look at things like some of the mesons, people describe them in terms of fluctuations between several different color forces and that. I would suggest no, that's actually overcomplicating the situation. That those are actually remnants of an earlier universe where there was less separation between those different forces, and that they form a single body, a single force that are just unified naturally. So rather than going to these incredibly high temperatures, I say, no, look at the stasis state of many of the things we see right now already is unified. You don't see these separations. You don't see these separations of all the colors and things like the mesons. You just see a single force that compactly puts them together. This would just be a suspicion or hypothesis, is I think we had a series of like burps of this CSU where you had a simple one that got to the point where it had some loops, and the loops started saying like, oh, I can spew something out, goes back together, but it doesn't completely lose this. I am following up on some of Penrose's ideas on this, by the way. But the idea that they come, they come apart and they go back together, that you get a buildup of complexity, and persistence persists. So you get another level where those forces I just mentioned, the ones that allow something like a pion to exist, they get broken up a little more pairs form, more breakout points form. You get another thing where you start getting the emergence of what you call a color force, where you actually get some orthogonality there. So you get another universe. It's a little more complex, still not enough to really do something. But my suspicion is that we are somewhere pretty far along in that process where the persistence has just gotten remarkably complex, and it's still a repeating cycle. So this is going back to Penrose's CCC, my variant of it. He doesn't use, I don't think he uses dual universes, but I have a dual universe version of his idea of these rescalings, but I don't do it by just expanding things. It's a different process of collapse and return. But I think I don't think it was just one event. I think there was multiple events, and it is continuing, but we reached a point in which time was so persistent that it can go for billions of years. And that's why we can look and see things that are so interesting. But I think that too eventually will come to an end. And that's I've got several figures on that quantizing general relativity presentation. Again, it's at Apibisky Notes, and I can't find my own presentation here. Let's see. Or at least that's nope. I seem to have I've got a wrong link in my file, so that's why I can't find it. Okay. Other questions?
Thanks for your explanation.
Was that another question, or was that a thank you? Okay. Other questions? I'm fine with calling it a wrap, folks. Whatever folks want to do.
Yeah, we can call off the meetup if you don't have any last minute questions. And Terry will give a talk on July 12th, the same time at noon.
Okay.
Sure.
All right.
Thank you for coming.
Thank you, everybody. Enjoy the questions, and really appreciate the interactions.
Thank you.